In this presentation, I will talk about the conversion of biomass research and plastic waste into value-added compounds. Nowadays, the development of sustainable and green process for the synthesis of pharmaceutical substance is one of the main challenges of the pharmaceutical industry. The direct connection of the drug center to biomass research provides an efficient and ecological approach for the sustainable production of a pharmaceutical substance. For example, the furan ring is present in many drugs possessing a variety of biological activities, and for this reason, the development of new methodology for the sustainable synthesis of furan derivatives is very important. In our group, we studied the synthesis of 7 furan derivatives from carbohydrates. Carbohydrates can be obtained from biomass research, and they are considered the ideal feedstocks for the production of many value-added compounds. In our group, we studied the one-pot synthesis of this furan derivative from the carbohydrate by in situ reaction of furfural. We began our work by studying the conversion of carbohydrates into furfural catalyzed by purinic acid. We studied, for example, the synthesis of the furfural from the xylose with the 18% yield in the presence of 5 more % of purinic acid in the dioxane at 114 degrees during 2 hours. Furfural is a very important chemical that is currently used for the production of many value-added compounds such as pharmaceutical herbicides and fuel. In our group, we also studied the synthesis of furfural from the polysaccharide silane, which is made from a unity of the xylose and is found in the synthesis of furfural from the polysilane. Involves in the first step the hydrolysis of the polysaccharides into the xylose, promoted by the aqueous solution of purinic acid, followed by in situ reaction of the xylose into the furfural with an overall yield of 68%. However, this reaction requires a high amount of the catalyst, 10 more %. Furfurylamines, the amines derived from the furfural, have diverse applications, including in the preparation of many biological active compounds and pharmaceuticals, such as the diuretic furosemide, commercially known as 6. In our group, we studied the one-pot synthesis of furfurylamines from the xylose, and these reactions involve the free reaction, and this chemical transformation involve free reactions in one pot, including the conversion of the xylose into the furfural catalyzed by purinic acid, followed by in situ reaction of the furfural with the anilines to produce the amines, and finally occurs the selective reduction of the amines using a silane as a reducing agent, which is activated by the presence of purinic acid in the solution. And this is the first example of the one-pot synthesis of furfurylamines from carbohydrates. We also studied the one-pot synthesis of furfurylamines from the xylose in order to study the general applicability of this methodology. And we studied the reaction of the xylose with the different anilines, and the reaction was performed in the presence of 5 more % of purinic acid in dioxane at 140 degrees during 2 hours in order to obtain the furfural. And then we added the aniline and the silane, and the reaction mixer was heated for more than 1 hour. And after the purification by column chromatography, we obtained all these furfurylamines with the overall yields between 56 and 18%. Then we studied the synthesis of furfurylamines from the polysaccharide xylanes, and this chemical transformation also involved 4 reactions in one pot, including the hydrolysis of the polysaccharide xylanes into the xylose. Different furfurylamines was also synthesized from the polysaccharide xylanes by a reaction of the xylanes with a variety of anilines, and after purification, these furfurylamines were obtained with overall yields around 60. We also studied the synthesis of alpha-aminophosphonates from carbohydrates. Aminophosphonates are structural analogs of amino acids in which the carboxyl moiety is replaced by a phosphonic acid or related groups. Aminophosphonates are very important compounds. They have very important applications. They are used, for example, as antiviral agents or as herbicides. And using a synthetic strategy similar to that developed for the synthesis of furfuramines from the xylose, we also studied one-pot synthesis of aminophosphonates from the xylose, and this synthesis involves the three reactions in one pot, including the conversion of the xylose into the furfural, catalyzed by pyrenic acid, followed by in situ reaction of the furfural with the anions to produce the amines, and finally we add a phosphate in order to obtain the corresponding aminophosphonates. And this is also the first example of the one-pot synthesis of alpha-aminophosphonates from carbohydrates. Due to the high importance of aminophosphonates, we also decided to study the synthesis of these compounds from the reaction of the xylones with the different anions and diethyl phosphate, and after purification of these aminophosphonates were obtained with moderated overall yields. Several aminophosphonates were also synthesized from the polysaccharide xylones, and this synthesis involves 4 reactions in one pot, and after purification, the aminophosphonates were obtained in the moderated yields. And in the market, there are several drugs containing a moiety formed by a furan ring linking to a different kinds of N-heterocyclic rings. For example, these antibacterial drugs has the furan ring linking to a quinazoline moiety. And this furan derivative containing a second heterocyclic ring, they are very important building blocks in the drug synthesis, but they are also compounds that usually display a wide variety of biological activities. And then we decide to apply our one-pot synthetic strategy to the one-pot synthesis of quinazolines from the xylose. Quinazolines are compounds that usually display a wide range of pharmacological and medicinal properties, and using our one-pot synthetic strategy, the xylose was initially converted to the furfural, catalyzed by pyrenic acid, followed by in situ reaction of the furfural with the different 2-aminocetophenols and ammonium acetate, and after purification, we obtain this furan derivative containing an quinazoline moiety with moderated overall yields. We have also studied the one-pot synthesis of dihydropyrimidones from the xylose. Dihydropyrimidones are also compounds with very interesting biological activities, and the synthesis of these compounds was obtained from the xylose by in situ reaction of the furfural with the different diketones or beta-keto ester using urea and thiourea as the nitrogen source. As conclusion of this first part, we have developed a one-pot synthetic strategy for the sustainable synthesis of furfuramines, aminophosphonates, quinazolines, and dihydropyrimidones from carbohydrates. And these methodologies allow the sustainable synthesis of furan derivatives containing nitrogen, phosphorus, and sulfur atoms from biomass derivatives that contain on carbohydrogens and oxygen atoms. And this one-pot multi-reaction process has also the advantage of minimizing chemical waste, reduced cost, time, and the separation of the intermediate compounds. And this work opens the possibility of applying different catalysts and synthesize a wide variety of furan derivatives, contributing to the development of more sustainable chemical and pharmaceutical industry. In the second part of this presentation, I will talk about our more recent work on the conversion of plastic waste into value-added compounds. Plastic is a remarkable material that has improved our life. It is present in the many of our everyday objects, including in packaging, in toys, sportwear, healthcare, car components, electrical and electronic goods, agriculture and construction, and in many other applications. The enormous consumption of the plastic has led to the generation of plastic waste, which has become one of the biggest problems all over the world. It is estimated that only 9% of all plastic ever produced have been recycled, and that about 79% were accumulated in landfills or in the environment. Plastic pollution has also a big impact on wildlife. For example, birds and marine animals can eat plastic, or they can get stuck into the plastic, which can cause the death of these animals. The slow degradation of the plastic on the environment releases microplastic and toxic chemicals. Microplastics are everywhere. They have been found in the oceans, in rivers, in drinking waters, agricultural soils, in the air, and also in fish we eat. It is estimated that people could be ingesting an equivalent of a credit card of plastic a week. Different kinds of plastic can degrade at a different time, but the average time of a single-use plastic bottle to completely degrade is at least 450 years. Some bottles can take up to 1,000 years to biodegrade. Plastic pollution represents not only a global environmental crisis, but also a loss of valuable research. A key strategy to overcome this problem is regarding the plastic waste as a potentially cheap source for the production of value-added compounds or as a raw material for the industry. Several years ago, we found that the dichlorodeoxymolybdenum complex is a very good catalyst for the reduction of a variety of aliphatic and aromatic esters into the corresponding alcohol, using a silane as a reducing agent with good yields. Based on this result, we thought that this catalytic system could also be appropriate for the reduction of several polyesters. And we decided to study the reductive depolymerization of plastic waste using the catalytic system, silanes, and dichlorodeoxymolybdenum complexes. We began our work by studying the depolymerization of this aliphatic polyester, polycaprolactone, using a granulated sample in the presence of 1% of the dichlorodeoxymolybdenum complex in the toluene at reflux, using the phenylsilane as a reducing agent. And from this reaction, we observed the formation of the 1,6-hexanediol with 85% yield. A similar result was also obtained using the environmental friendly polymethyl hydroxysiloxane. And then we decided to study the possible use of this catalyst in the multiple catalytic cycle in the depolymerization of a polycaprolactone. And we found that this catalyst can be used in at least 8 catalytic cycles with good yields between 85 and 79%. Then we decided to study the depolymerization of another aliphatic polyester, polylactic acid, and this reaction was initially studied using a sample obtained from a plastic cup cut into small pieces, and the reaction was performed using 1% of dioxymolybdenum complex in the toluene at reflux, using phenylsilane as a reducing agent. After 20 hours, we analyzed the NMR spectrum of the reaction mixer, and we observed that all the polylactic acid was reduced, and that the signal of the signal of the expected product, the propanediol, were not observed in the NMR spectrum of the reaction mixer. The only signals observed in this spectrum corresponded to the solvents, to the reducing agent and the internal standard, and no product was identified at the end of the reaction. And these results suggest the formation of the propene gas by in situ reduction of the propanediol. The formation of propene gas was confirmed by GC. We also tested this reaction in the depolymerization of a sample obtained from a filament wasted from a 3D printer, and we also observed the formation of propene gas, and the reaction was not affected by the presence of the pigment in the sample. To confirm the formation of propene gas as a result of the in situ reduction of the propanediol, we decided to study the reduction of this diol with this catalytic system, and we also observed the formation of propene gas at the complete reduction of this diol. The production of the propene gas from the polylactic acid is a very important result because this polyester is derived from biomassa research, and this reaction can contribute to reduce the production of the propene gas from fossil sources. Then we started the depolymerization of polyethylene terephthalate, PET, which is the most common polyester used. And initially, the reaction was studied using a sample obtained from a Evian water bottle, finally ground. And as each PET monomer containing two ester groups, this reaction was performed with a high amount of catalyst, 5% of dioxamolybdenum complex, and also a high amount of the reducing agent, 6 equivalent. And due to the low solubility of the PET, the reaction was performed at a high temperature at 160 degrees during 4 days. And as product, we observed the formation of paraxylene and ethylene glycol with 65% yield. To confirm the formation of paraxylene from the reduction of the PET, we also decided to study the reduction of the PET monomer with this catalytic system, and we also observed the formation of paraxylene and the complete reduction of this compound. These results also suggest that this catalytic system, the phenylsilane and dioxamolybdenum complex, can also be used to deoxygenate aromatic ester into the corresponding alkyl benzene derivatives. Our next goal was to study the depolymerization of textile waste. Globally, about 92 million tons of textile waste is created each year. As the polyester is the most popular fabric used in fashion, it is also very important to develop efficient methodology for the valorization of textile waste. And we decided to test our reaction in the depolymerization of two samples, one obtained from a sport jersey and another obtained synthetic pillow filling, and using the same reaction condition applied in the depolymerization of the water bottle. And as a product, we also observed the formation of paraxylene and ethylene glycol with 65 and 62% yields. Our next goal was the depolymerization of the polybutylene terephthalate, PBT. PBT is the second most used in polyester, and PBT has a structure similar to the PET, containing a carbon chain with 4 carbon instead of 2 carbon. The depolymerization of PBT was initially studied using a granulated sample, and the same reaction condition applied in the depolymerization of PET, and as product we observed the formation of the paraxylenes and 1,4-butanediol. As PBT is used for the production of many car components, we also decided to study this reaction using a small amount of an engineered component of a car, and we also observed the formation of these two products. Consider that most of plastic waste are composed of a mixture of different polyester. We also decide to study the selective reduction of a mixture containing these three polyester: polycaprolactone, polylactic acid, and PET, using 2 mole% of dioxamolybdenum complex and 6 equivalents of polymethylhydroxysiloxane at 110 degrees during 2 days. And then we analyze the reaction, the NMR of the reaction mixture, and we observe that the polylactic acid was completely reduced, producing the propene gas, and the polycaprolactone was also reduced, producing the hexanodiol, and it is possible to see the signal of the hexanodiol in the spectrum of the reaction mixture, but we did not see any product from the reduction of the PET. And this result demonstrated that under this reaction condition, PET is not reduced and become insoluble in solution. And these reactions allow the selective depolymerization of these three polyester, leading to the separating the production of the hexanodiol, which remain in solution, and also produce a gas, propane gas, and PET remain insoluble in the solution and can be removed by filtration and reduced separately. The results obtained using the dichlorodoxamolybdenum complex as catalyst demonstrate that this complex is a very efficient catalyst for the valorization of real plastic waste and into several value-added compounds with good yields. In the continuation of this work, we decided to study the use of the zinc acetate as catalyst for the depolymerization of plastic waste, because zinc acetate is an environment-friendly, commercially available, and very cheap catalyst. The use of zinc acetate as a catalyst was initially applied in the depolymerization of polycaprolactone using a graduated sample. This reaction was performed in the presence of 5 mole% of zinc acetate in the toluene at reflux using these two reducing agents, and the hexanodiol was obtained with 98% yield. Then we also studied the use of zinc acetate in the multiple catalytic cycles in the depolymerization of polycaprolactone, and we found that this catalyst, zinc acetate, can be used in at least 7 catalytic cycles with good yields. Then we evaluated this catalytic system, phenyl silanes and zinc acetate in the depolymerization of the polylactic acid, and this reaction required 10 mole% of zinc acetate and 3 equivalent of phenyl silanes. The reaction was performed in toluene at reflux, and from this reaction we did not obtain propene gas, but we observed the formation of propanediol. This reaction was performed using 2 different samples, one obtained from a plastic cup and another obtained from a filament waste from a 3D printer, and the propanediol was obtained with 71 and 6% yields. The production of propanediol is also very important because this diol has many applications in the chemical, cosmetic, and pharmaceutical industry. This catalytic system was also tested in the depolymerization of 3 PET samples, and the reaction was studied using 10 mole% of zinc acetate and 6 equivalent of phenyl silanes at high temperature at 160 degrees during 4 days. And from this reaction, we observed the formation of paraxylene with HREOs around 60 and ethylene-glycol with HREOs around 40. And finally, we also apply the system of neosilane and zinc estates in the depolymerization of a PBT sample. And the reaction was also studied under the same reaction condition used for the depolymerization of PET from two different samples, a granulated sample and a car component. And from this reaction, we observed the formation of paraxylenes, and instead of the expected 1,4-butanediol, we observed the formation of tetrahydrofuran as a result of the in situ selectivization of the butanediol. As conclusion of this second part, we have developed two novel methodology for the reductive depolymerization of several plastic wastes using that morodioxamolybdenum complex and zinc estate as a very efficient, cheap and environmental friendly catalyst. And this catalytic system proved to be efficient for the depolymerization of a variety of real plastic waste and or obtaining from domestic waste or generated from a different industry. And we believe that this work can contribute to reduce the large amount of plastic waste that is released into the environment or into the ocean, and can also improve the circular economy and the human health. Finally, I would like to thank the students that performed this work. João Caetano synthesized the furfuramines, PhSiH studied the synthesis of the aminophosphonates, Carolina Carreira investigated the synthesis of quinazolina and dihydropyrimidinones, and Beatriz Nunes studied the depolymerization of plastic waste with the molybdenum complex. I would like to thank to Dr. Conversão Oliveira for the mass spectroscopy study, to CKA, and to the FCT for the financial support, and all of you for your kind attention.